In this problem, we're asked to figure out the strength of the electrostatic force between an electron and proton that are part of an atom, and then determine the gravitational force between an electron and proton that are part of an atom. And in both, we're assuming that the two particles are 1 nanometer apart. A nanometer is 1 times 10 to the negative 9 meters. So we can do these in either order, I suppose. The problem asked us to do the electrostatic force first. So there's a bunch of stuff that you either need to look up or Google in doing this. If this were an exam, those numbers would be provided on the exam. But the force between charged objects is equal to a Coulomb constant. Coulomb constant was given in lecture 25, and it is 8.99 times 10 to the 9th. Has some odd units, but the units are what are needed to cancel out most of the units of the other factors in here. Newton meters squared per Coulomb squared. The charge on object 1, well, I would need to know the charge of an electron. It turns out you can look up the charge of an electron fairly easily. You can ask Siri or whatever device, look it up on Google. It is 1.6 times 10 to the negative 19 coulombs. And the charge on a proton is the same amount of charge, just opposite in sign, so that when you have equal numbers of protons and electrons, the atom is electrically neutral. The distance we're assuming here is 1 nanometer, so that's 1 times 10 to the minus 9 meters, and that's all going to be squared. And so note that meters squared is going to cancel meters squared here. Coulomb times a coulomb is going to give me coulomb squared, which cancels coulomb squared here. I'm going to end up with a number that's just in newtons, which is what I would want for measuring the force. So 8.99 times 10 to the 9th times 1.6 times 10 to the negative 19th times 1.6 times 10 to the negative 19th, and then I'm going to divide that by 1 times 10 to the 9th, 10 to the negative 9th, squared, and I will get the size of that electrostatic force. That's about 2.3 times 10 to the negative 10 newtons. So that's a fairly small force in the context of things we're thinking about in our everyday life, but of course we're also thinking here about two particles in an atom, which are very, very, very tiny. So that is actually turns out to be not an insignificant force. And so to contrast, let's work out what the gravitational force is between an electron and a proton. So the gravitational force is determined by the Newton's law of universal gravitation, which was first mentioned way back in lecture 11. And it is very similar in form to the Coulomb force law, but it has a different constant. You can Google, and the gravitational force constant is 6.67 times 10 to the negative 11, and its units are Newton meters squared per kilogram squared, because gravitational attraction depends on mass, unlike charge in the electrical problem here. Again, Google or some other device makes it fairly easy to look up the masses of a proton and a mass of an electron. A proton is about 1.67 times 10 to the negative 27 kilograms, and an electron is about 9.1 times 10 to the minus 31 kilograms. It is much, much less massive than a proton or a neutron. And we're still assuming for the purposes of this problem that things are a nanometer apart. So let's go ahead and punch that into the calculator. So 6.67 times 10 to the negative 11 times 1.67 times 10 to the negative 27 times 9.1 times 10 to the negative 31 divided by 1 times 10 to the negative 9 quantity squared, and I get a ridiculously small number, 1.0 times 10 to the negative 49 newtons. In addition to giving us practice in, calculating those forces using those formulas, this allows us to make an important conclusion about atoms. When we're talking about phenomena that are on the atomic level, we don't really need to worry about any gravitational effects. Any gravitational effects that would be in an atom are dwarfed by many, many, many orders of magnitude by electrostatic forces. And then if we're talking about within the nucleus, those forces in the nucleus are, the electrostatic forces are dwarfed by the strong nuclear force. So the punchline is gravity doesn't matter on the atomic scale. The electrical forces in an atom do matter though, and today we're talking about another phenomena that ultimately is the result of moving electrical charges within the atom.